Thank you very much. It's always a pleasure to be here. So, I think to start that we can all agree that there is a crisis in education, and we can also probably agree that the crisis is not new. Recently, I was reading an essay by Hannah Arendt of that same title, The Crisis in Education, from 1968. And it is very interesting that since then, essentially nothing seems to have changed. Well, as far as the general philosophical assumptions guiding education are concerned. Many consequences have unfolded, but the premises have remained roughly the same. Arendt attributes the crisis to what she calls the bankruptcy of progressive education in the context of a mass society. In her view, progressive education is based on three fundamental assumptions. The first assumption is that education should respect the autonomy of the children's world and emancipate it from the authority of the adults. It is a sort of democratization of education which has the undesired effect of handing each child to the tyranny of his or her peers. That's Arendt's critique. The second assumption is the primacy of pedagogical method over material content in the formation of teachers. This is something that strikes every European when they get off the plane, right? That teachers are trained to be teachers before they're trained to be mathematicians or physicists or historians or whatever. The teacher's knowledge of what they teach is of secondary importance in education schools compared with their ability to facilitate the children's efforts to learn by themselves. The third assumption is the replacement, Arendt says, as the end goal of education of imparting knowledge with the inculcation of skills. This is, of course, the pedagogical inheritance of American pragmatism. Pragmatist education aims not to transmit dead knowledge or rote learning, you probably heard these formulas, but to teach children how to do things and achieve practical goals. Knowledge is necessary in a purely utilitarian sense, not because it has any intrinsic value, as knowledge of the true, the good, the beautiful, but because it is necessary for the development of skills. I also do not think I need to convince you that still today this philosophy holds sway over American pedagogy, and that by and large it has led to poor educational outcomes, especially for less privileged students. You know, this kind of progressive utopia always has a paradoxical effect of hitting the ones it most would like to help, the most underprivileged parts of society, because rich people usually have ways to work around the problems. Mathematics has probably been the biggest rock on which the ship of progressive education has floundered. At the K-12 level, the American system produces an unusually high fraction of mathematically unprepared students or underprepared students compared to other developed countries, except for the growing list which has embraced the American model. At the college and university level, mathematics and the sciences that depend on it, the so-called STEM disciplines, have achieved a sort of strange elite status based on the fact that a relatively small fraction of students, compared to the past and to other countries, have the necessary mathematical background. So much for, again, democratic and egalitarian education. The truth behind this situation is that by its very nature, mathematics is philosophically at odds with the anti-authoritarian pragmatism described by Hannah Arendt. In another essay, she observes that authority implies an obedience in which men retain their freedom. Thus, authority is, first of all, an attribute of self-evident truth, because self-evident truth compels the mind, but in this coercion, it needs no violence to be effective. And it's not stronger than, it is stronger than persuasion and argument. In particular, mathematical truths demand reason's obedience while respecting its freedom, because by nature, reason finds its fulfillment in knowledge. Due to its authoritative nature, mathematics is very hard to democratize. Its authority transfers to the teacher, who has mastered it, and it is hard to learn without his or her explicit guidance. Mathematics also resists being reduced to a practical utilitarian activity. Learning mathematics requires genuine conceptual understanding. It cannot be reduced to performing formal manipulations. without understanding the conceptual framework and the purpose of the theory. Otherwise, the inevitable result, which I meet every day, is that the students are at a loss when faced with problems even slightly different from those they have already solved before. More fundamentally, without conceptual understanding, they do not truly learn math. And what they learn, they forget very quickly. Because of this undemocratic and non-pragmatic nature of our discipline, today a university math department is often in the curious and uncomfortable position of being the bastion of authority on campus. We can still claim that what we teach is simply true. We can still tell the students, this is right and this is wrong, especially the second part. Right. You learn, you did not learn. You pass, you fail. And they have to accept it for the most part. This does not make us popular with the administrators because we spoil their beloved data about student success. On the other hand, many colleagues in other departments secretly count on us to stop the most unprepared and unmotivated students from coming their way. We derive no pleasure from this role, believe it or not. No, I'm sorry. Nobody likes to be told that ours are the killer courses or that we ruin people's lives. No, wait. I've been told both. But at the end of the day, we must stand for the basic principle that without knowledge and understanding, there is no education, regardless of how many people receive a diploma. The unnaturally deep division I mentioned before between the students who can do math and those who cannot, you could say the mathematical haves and the have-nots, is reflected in a split between how we teach mathematics for liberal arts programs and for scientific and technical majors. On the one hand, liberal arts programs seem to attract almost exclusively students interested in the humanities and the social sciences. These students are usually required to take one or two kind of token math classes. This can be either the so-called college algebra courses, which is kind of a revisitation of high school math, or statistics courses for the social and human sciences, or classes dedicated to fun and useful mathematical concepts, also known as quantitative literacy courses. When you hear these kind of words, they come from a PhD in education. On the other hand, well, sorry, any PhD, I don't want to offend the PhDs in education. But on the other hand, this is for the humanities side. On the other hand, students in scientific and technical fields are pushed very early to embrace a high degree of specialization. They receive a substantial math education, but it is entirely directed to the study of their disciplines without the liberal art dimension, both in the sense that math courses are not integrated with the curriculum in the humanities, and in the sense that math is presented chiefly as a tool for science and technology and disconnected from any broader cultural or philosophical context. What seems to be lacking, including at many Catholic institutions, is a comprehensive curriculum that both imparts STEM-oriented students with the technical knowledge needed for subsequent studies and integrates math and science within a classical liberal arts education. So I'm going to discuss what are the guiding criteria for this possible integration. What is this integration possible? Here I would like to quote again the sentence that Father Antonio already quoted yesterday by Jungmann about education as an introduction to total reality, right? So if we want to use the definition of education, the question of the integration is related to what aspect of total reality does math introduce us to? Because if we understand what precisely are the aspects of total reality that we are dealing with, it will be easier, hopefully, to make the necessary connections. I want to focus on two such aspects which I think are particularly valuable. First of all, mathematics introduces us to what I would like to call the realm of certainty and necessity. These two words indicate the subjective and objective sides of the same phenomenon. In mathematics, the experience of certainty stems from contemplating the necessity inherent in the sphere of pure mathematical ideas. An author, which I'm going to quote, who emphasized this quote, kinship between necessity and certainty, end of quote, was Simone Weil, whose brother André Weil was a brilliant mathematician. She was very jealous of him. In her works, the concept of necessity plays an important role, well beyond mathematics, because to Weil, necessity manifests God love in the created world. Necessity shows that the world is under the rule of the Platonic logos, which never, for instance, abandons reality to chaos. Weil felt a strong affinity for ancient Greek mathematics, which since the beginning had a symbolic and even religious significance. In one of her notebooks, she writes that for the Greeks, mathematics was foundation of religious certainty, and that, quote, invention of demonstrative proof was due to the Greeks' need for certainty in regard to divine things. Numbers were privileged image of divine things because of their certainty, right? Their certainty gave them a religious connotation, end of quote. She further claims that the history of mathematics has been an introduction to faith, from the less to the more certain, and from the more to the less representable, as exemplified, for instance, by the discovery of irrational numbers. Another quote, it was because of their faith inspired by Christ's love, that the Greeks had that hunger for certainty, which made them invent the geometrical proof, end of quote. Elsewhere she wrote, quote, pure science is the contemplation of the order of the world as necessity. Necessity only appears through the method of proof. That this mathematical necessity should be the substance of the world, this is the sign of our Father. All of this has a moral counterpart. In order to have access to the truth, that was the end of the quote, now it's me. All of this has a moral counterpart. In order to have access to the truth, the mathematicians must submit to mathematical necessity, to the liberating power of evidence. Weil again noted that there is also an, quote, obvious kinship between the idea of necessity and obedience, end of quote. Thus, the study of mathematics forces us to face a deep mystery. What we desire the most, truth, can only be achieved by accepting the constraint of necessity. Freedom is fulfilled through obedience. In this case, obedience to the undeniable evidence of the proof. And not only truth is the fruit of such obedience, but beauty as well. Weil again, quote, the main source of mathematical beauty is the docility of mathematical beings. What to us is resistance is not caprice, but docility to their law, end of quote. Mathematical objects may resist our understanding, but they are completely docile to the proof. This is the source of a common experience of mathematicians, that when a mathematical problem is well understood, it takes the appearance of simplicity. No matter how obscure a problem may appear to be, once it is solved, it immediately attains a status of great clarity, without shade or doubt. This clear, almost luminous, harmonious submission of the parts to their necessary relationships is the source of mathematical beauty. And when it is missing, a mathematical theory feels unsatisfactory, still incomplete. In this sense, last quote from Weil, the object of science is the exploration of the beautiful a priori, end of quote. So this was the first aspect of reality to which mathematics introduces us. Whereas this first aspect of reality that mathematics discloses to us was already recognized by the Greeks, the second aspect I want to discuss is essentially modern and can be summarized in Galileo's claim that the book of nature is written in mathematical language. If for the ancients mathematics introduces us to the divine, for the moderns it provides the key to a different and surprising contemplation of nature. Natural phenomena turn out to follow certain mathematical patterns, which the human mind can grasp and verify experimentally. These patterns can be built into general theories, which are necessarily incomplete because they only apply within certain ranges of the experimentally measurable quantities. Nonetheless, within the domain of validity of a theory, scientists observe that nature follows mathematical laws, often to an amazing degree of precision. The agreement with the experiment is the criterion the scientists must use in order to develop the mathematical description. This introduces a different sort of moral element in the scientific enterprise. Mathematical models must obey the experimental data to produce a good theory. As I tried to explain on some other occasions, this mathematical description of nature is intrinsically abstract, meaning that by its very method must concentrate on some limited features of our experience of nature, those which can be measured and verified quantitatively. This process of abstraction presents some serious dangers. First of all, it can lead to positivism, the misguided idea that the measurable and verifiable facts are all we can know about nature. This forgets that our experiments and observations are inextricably linked with our theories, which in turn are subordinate to our broader, antecedent experience of the natural world as intelligible, beautiful, interesting. The positivist has to forget all of that. Secondly, by making natural phenomena to some degree predictable, the mathematical study of nature lends itself to what we might call the Baconian temptation, from Francis Bacon, the pursuit of domination over nature itself. This leads easily to the technological and instrumentalist mindset which has become so prevalent in the modern world. Despite these dangers, I maintain, based on my own experience and the history of science itself, that the mathematical approach to the natural sciences is not per se incompatible with the sound philosophical understanding of the natural world. I will go even further and claim that this approach starts from an essentially contemplative impulse, which can be observed in many great scientists, like Galileo himself. The sad irony is that such contemplative impulse of the scientists has been foreign to some of the modern philosophers, who turn science into an idol. Think of some of the men of the French Enlightenment, Condorcet, that kind of person. Far from denying the beauty and mystery of nature, the mathematical descriptions adds, in my view, an extra layer of intelligibility, which is itself beautiful and mysterious. In fact, I think that the discovery of mathematics at the heart of material reality itself is surprisingly consonant with the old Greek idea that mathematics is a window open to the divine. To explain what I mean, I want to quote a book that many of you are familiar with, Introduction to Christianity, where Joseph Ratzinger claims that Christian faith itself, quote, means first the decision in favor of the primacy of the logos as against mere matter. It means the view that thought and meaning do not just form a chance byproduct of being, that on the contrary, all being is a product of thought, and indeed, in its innermost structure, is itself thought. Ratzinger goes on to say, quote, in the old Pythagorean saying about the God who practices geometry, there is expressed the insight, that insight into the mathematical structure of being, which learns to understand being as having been thought, as intellectually structured. In our time, still Ratzinger, through the investigation of the mathematical construction of matter and the way it can be conceived and evaluated in mathematical terms, this insight of the Pythagoreans has gained an amazing solidity. Einstein said once that in the laws of nature, quote by Einstein inside the quote by Ratzinger, an intelligence so superior is revealed that in comparison all the significance of human thinking and human arrangements is a completely worthless reflection. End of Einstein quote. Now back to Ratzinger. This surely means that all our thinking is indeed only a rethinking of what in reality has been already thought beforehand. The mathematical understanding of the world as here discovered through the mathematics of the universe, so to speak, the God of the philosophers. That's the end of the long Ratzinger quote. The God of the philosopher, of course, is not the incarnate God of revelation. Ratzinger says that this is to be expected because, quote, the completely superfluous wonder of beauty will never be discovered by physics and cannot be, because in its investigation it abstracts, in accordance with its nature, from the aesthetic feeling and from the moral attitude, questions nature from a purely mathematical point of view, and consequently can also catch a sight only of the mathematical side of nature. The answer depends simply on the question, end of quote. I completely agree with Ratzinger because physics does not know beauty. However, the physicist does know beauty. Physics. So I would make one important amendment, that the mathematical side itself has its own beauty. It reveals a deeper harmony at the heart of nature, which, in the words of the great physicist Henri Poincaré, cannot be grasped by the senses, but only by pure intelligence, the human ability to contemplate pure ideas, right? I mean, a lot of physicists, I remember Feynman said the same thing. You can look at nature and appreciate the beauty of the moon. Now, if you understand Kepler's solution to Newton's equations, the moon is still beautiful, but there is an extra layer of beauty to the moon. To sum up, and I'm getting close to the end, I have identified two ways in which mathematics introduces us to total reality. One, the experience of certainty associated with the contemplation of necessity. And second, the discovery of harmonious structures embedded in natural reality. In both cases, the word obedience came up. First, in the sense of obeying the evidence of rigorous mathematical proof, and then in the sense of submitting the theory to experimental evidence. These are, if you wish, two forms of morality built inside mathematical thought in its pure and applied versions. Corresponding to these two forms of morality, two forms of beauty also came up. The beauty of mathematical necessity and the beauty of the mathematical harmonies discovered in nature. I think that these three pairs, the cognitive, the moral, and the aesthetic, give us the guidelines to develop a rich and meaningful liberal arts math curriculum. The student should be introduced both to rigorous proof-based mathematics and to math-based descriptions of the physical world. They should be made aware of the moral dimensions of both mathematical proof and mathematical modeling. And above all, they should be taught to admire the beauty of both the abstract architectures of pure mathematics and the harmonious mathematical structures of the cosmos. Now, this was essentially the conclusion of my talk. I also wrote an appendix. How did I do with time?
You still have 5 minutes.
5 minutes? I'll give you the appendix. Okay. No, because I was thinking that question. How do you integrate the, in a liberal arts context? You want to run to a liberal arts college and you want the students to do some serious math in a philosophical and theological context. What is the best math? Now, for centuries, for even millennia, the proof aspect of teaching math in a liberal arts context has been the study of Euclidean geometry, which is a classic. And this is a wonderful tradition, which in my opinion should be carried on, but probably could be carried on at the high school level. It does cover what I call the first aspect of teaching mathematics, but it does not lend itself to introducing the student to the second aspect, the one that has to do with science and nature. As an alternative, I want to propose a concept suggested to me by a book which randomly appeared on my desk while I was preparing this talk. I said, oh, look, what is that? It was my wife. It was not, but it's still a science, so I said, it was a book that was donated to me from a dear and bibliomaniac friend of mine who passed away in 2020, Tom Sullivan. Anybody in the room got a book from Tom Sullivan? Oh, he was a good guy, but he used to give away used books to everybody. Anyway, this book is a book that is like a book about Einstein's general relativity for dummies. And it made me think that a rewarding way to teach math to liberal arts students would be to combine the study at a suitably elementary introductory level of 1, mathematical analysis, 2, Riemannian geometry, and 3, general relativity. Mathematical analysis, which is the rigorous form of what is commonly called calculus, would be the place to learn about mathematical proof, because it is as rigorous as Euclidean geometry, but it is different and simple enough. The application of analysis to the study of surfaces and other curved objects, Riemannian geometry, would take care of the geometric education. In turn, and we come to the second aspect, Riemannian geometry is the mathematics that underpins our most general, powerful, and beautifully elegant physical theory of the universe, general relativity. Finally, a senior year introductory course on general relativity and cosmology would go well together with an interdisciplinary capstone course on visions of the universe in physics, philosophy, and theology. Okay, this appendix was just one possible an admittedly unconventional idea, but it was just meant to exemplify that we have to strive for this integration of the pure and the applied, the cognitive, the moral, and the aesthetic. And so that would be the goal. Thank you.